So this question is about simple harmonic motion. Let's just quickly go through it. A small metal pendulum bob is suspended at rest from a fixed point with a length of thread of negligible mass. The pendulum begins to oscillate. Assume that the motion of the system is simple harmonic and is in one vertical plane. The graph shows the variation of kinetic energy with time. So the first question is, calculate in meters the length of the thread. State your answer to an appropriate number of significant figures. So looking in the data booklet, you come up with this equation. The period time of a pendulum is equal to 2 pi times the square root of L over G. But it's obvious to be able to calculate length, we need the period time. So if we go back through our graph here, the period time is actually 2.25. There's a common mistake here that loads of people think the period time is actually this point here. But if we just sketched an example of one complete oscillation, the pendulum would go all the way there and then back again like that. And so you can look at this graph and see that the kinetic energy goes from a maximum to a minimum, maximum, minimum, and maximum again in one complete cycle. It starts off minimum all the way back and so forth. So the period time is 2.25 seconds. Putting all those bits of information into my equation, I end up with an answer of 1.26. Now, is that an appropriate number of significant figures? Yes, it is, because the data that I've got from the graph is to 3 significant figures. The information is also I've got from my data booklet for G is 3 significant figures, so that's okay at 3. I would accept 2 significant figures here in an answer of 1.3 meters. The second part of this question, it says label on the graph with the letter X a point where the speed of the pendulum is half the initial speed. So I've just written this expression that kinetic energy is proportional to V squared, because what I've been given here on the graph, I've got a graph of kinetic energy. So if kinetic energy is proportional, if EK is proportional to V squared, I want to figure out the point where the speed of the pendulum is half that of the initial speed. Well, that's going to be a point where the kinetic energy is actually a quarter of the initial kinetic energy, because if I've got 1 over 2 all squared, I'm going to get 1 over 4. So a point at any, as I've labelled here, any position along the graph would give you the mark. Moving on to the second bit. Now the second bit of this question is to do with kinematics. So let's just read it. When the 75 kg bob is moving horizontally at 0.8 meters per second, it collides with a small stationary object, also of mass 75 grams, and they stick together. So here's the diagram. And the question is, calculate the speed of the combined masses immediately after collision. So immediately I know if it's a collision, it must be something to do with conservation of the momentum. So the momentum before equals the momentum after. Initial and final momentum are the same. So the momentum before is mass times velocity. Well, there's the velocity of the pendulum bob. That was its mass. I've left it in grams. It doesn't matter in this situation. So then they move off together with a combined velocity v and a combined mass 150. So the answer comes out as 0.4 meters per second. Then finally in this question, show that the collision is elastic. Well, to do that, we have to look at the initial kinetic energy and compare it to the final kinetic energy. So when I do that, the initial kinetic energy of the system is a half times the mass of the pendulum bob times its initial speed, and I get this 0.024 joules. Final kinetic energy, half times the overall mass of both of those objects moving together, and then their overall, so their combined speed is 0.4, which we've calculated previously, and I get an answer of 0.012. So it is not an elastic collision, it's actually an inelastic collision, and you've shown that because energy is lost in an inelastic collision. So the collision is inelastic.